We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal...
64 years ago, a president made a promise that seemed impossible. America kept it. Now NASA is making another one they call close to science fiction. Near impossible, according to Carlos Garcia Galan, Moon-based program executive.
Good morning, everybody. I'm Carlos Garcia Galan. I'm your Moon-based guy.
When you look at this picture, it's very clear that to execute this vision, we're going to need to achieve the near impossible. But this is what we do. We're NASA.
Landing on the moon remains one of the most technically demanding achievements in human history. In the last 5 years alone, Israel crashed, Russia crashed, Japan crashed. Multiple American commercial landers reached the moon with mixed results at best. The lunar South Pole, the target of every serious program on Earth right now, wasn't successfully reached until India landed there in 2023. The history of this effort is humbling. 6 decades, $107 billion in inflation-adjusted dollars spent on plans, programs, and promises that never delivered a base.
Ignition and liftoff of Ares 1S, testing concepts for the future of new rocket design.
The Constellation program, NASA's post-Apollo lunar return initiative, was canceled in 2010 by the Obama administration.
Yes, pursuing this new strategy will require that we revise the old strategy. In part, this is because the old strategy, including the Constellation program, was not fulfilling its promise in many ways.
Strategies reversed, administrations pivoting. So why now? China's 2020 sample return mission found helium-3 embedded in a previously unknown lunar mineral, an isotope virtually non-existent on Earth, potentially abundant across the lunar surface, and a theoretical fuel for fusion reactors that could power civilization for centuries. China isn't going to the moon for bragging rights, neither is anyone else.
But this time, the goal is not flags and footprints. This time, the goal is to stay.
The mandate from the administration is explicit: return Americans to the moon.
NASA has the enthusiastic interest of President Trump, the Vice President, the Cabinet. We have bipartisan congressional support. We have a national space policy outlining the most righteous and inspiring objectives.
Establish an enduring presence and do it faster than anyone thought possible. The urgency is real.
America will never again give up the moon. That brings us to the next step: building the moon base.
How do you build a permanent city on the moon?
We're going to have to deploy systems in very high cadence that will survive extremes in temperature, illumination, and very complex and rugged terrain with very steep slopes.
NASA's response is a 3-phase, $20 billion plan targeting the lunar South Pole, chosen for confirmed water ice, near-permanent sunlight, and its strategic position.
The moon base will not appear overnight. We will invest approximately $20 billion over the next 7 years and build it through dozens of missions, working together with commercial and international partners towards a deliberate and achievable plan.
Robots arrive first, testing power systems, mobility, and communications. Nuclear power solves the 14-day lunar night at -173 degrees. Semi-permanent infrastructure follows, then permanent habitats with hardware contributed by Japan, Italy, and Canada. LunaNet will provide internet-like communications across the surface. Commercial contractors will deliver much of the hardware. The nuclear technology proven here will power the spacecraft launching toward Mars in December 2028.
As Administrator Isaacman announced, the nation is getting underway in space on nuclear power, and we will start by flying a nuclear electric propulsion demo to Mars in December 2028.
Radioisotope heating units, small nuclear devices using plutonium-238, will keep critical equipment operational through the long lunar night.
We're going to have to build systems that also provide power, mobility, and habitation around those places, and also consider lighting. Like you see today, some of these areas that are very interested for science and exploration are sometimes permanently shadowed or have significant length of shadow periods. So having systems there that can survive the temperature gradients that we're going to see and the lighting are going to be critical.
The Lunar Gateway, NASA's original plan for an orbital station around the Moon, has been paused. The hardware already built will be repurposed, the workforce redirected. The priority is now the surface, not the orbit. An orbital structure remains a possibility for future logistics needs. For now, the base comes first. The location is not arbitrary. The lunar South Pole was chosen for reasons that are both scientific and practical. Permanently shadowed craters at the poles contain confirmed water ice, the most valuable resource on the Moon. Water means drinking water. Water means oxygen. Water means hydrogen fuel. The supply chain for a lunar base depends on what can be extracted locally, not shipped from Earth at extraordinary cost. Named after the lunar program, NASA has a name for it already: Artemis Base Camp. But the South Pole presents engineering challenges that have no precedent in human construction history. The lunar night lasts 14 Earth days. During that period, temperatures drop to -173 degrees Celsius. Equipment not designed to survive that cold simply fails. Every rover, every drone, every habitat element must be engineered for an environment that would destroy conventional technology within hours. The 3 phases of base construction reflect the scale of what's being attempted. Phase 1 runs from 2026 to 2028. The focus is reliability, getting to the Moon consistently, learning from each landing, delivering the equipment that tests power systems, mobility, communications, and navigation. Up to 25 launches, 21 landings, delivering approximately 4,000 kilograms of hardware. Rocket-powered drones called MoonFall will scout terrain no rover can reach, mapping the South Pole crater by crater before construction begins. Phase 2 begins in 2029. Infrastructure arrives. Semi-habitable structures, Japan's pressurized rover, a vehicle astronauts can work inside without spacesuits during extended traverses. Communication relay satellites providing continuous contact with Earth even from the far side of the base location. 27 additional launches, 60,000 kilograms of cargo. Phase 3 delivers the permanent infrastructure, full habitats from Italy's space agency, a lunar utility vehicle from Canada, nuclear and solar power systems at scale, a cell phone-like surface communications network, a lunar GPS system. Continuous human presence becomes the operational reality rather than the aspiration. The suits that astronauts wear, and eventually, the infrastructure that reduces their dependence on suits during surface operations, represent another engineering frontier. Current spacesuits provide limited mobility and limited endurance. Phase 2's pressurized rover is specifically designed to extend the operational range of astronauts beyond what a suit alone allows. Oxygen production, water extraction, and in-situ resource utilization, using what the Moon provides rather than shipping everything from Earth, are central to Phase 2 and 3. Lunar regolith processed into building materials. Scientific research remains embedded throughout. NASA's Science Directorate has not been sidelined by the strategic urgency. The Moon base serves as a research platform. Geological studies, heliophysics observations, radio astronomy from the far side, biology of long-duration human presence in deep space.
We are determined to do more science than ever. My favorite, the iconic pale blue dot image from a distance of 3.7 billion miles away, and now the first spacecraft to have left the protective bubble provided by our sun and traverse into interstellar space.
The ambition invites scrutiny, and the scrutiny is legitimate. $107 billion already spent on plans that didn't deliver. The new commitment asks for $20 billion more, with the full 3-phase program potentially reaching $30 billion. The funding pathway beyond the initial allocation remains incomplete. NASA's own science leadership acknowledged the trade-off directly: reduced safety protocols, managed risk. In an agency that carries the memory of Challenger and Columbia, those words carry weight. Some of the technologies NASA has outlined don't yet exist. Garcia Galan was candid about that. The plan accounts for discoveries that haven't been made yet, which is either the definition of ambition or the definition of optimism, depending on your perspective. Private investment is expected to absorb increasing costs as the infrastructure matures. The commercial model requires revenue that doesn't fully exist yet. The return on investment from space exploration isn't always visible, until the day it suddenly, urgently is.